In this video, we're going to do some problems to review for the first test in BC Calc, polars and vectors. So our first problem is to give 4 different polar coordinates with the theta going between negative 2 pi and positive 2 pi, and here are our rectangular coordinates. Now I'm going to graph these, but you don't have to. You could do all this without actually drawing the picture, but I think sometimes visualizing it helps you figure out what to do here. So we're trying to find the r and the theta. So the r is our hypotenuse, or it's just the square root of x squared plus y squared. And so we're going to get 9 plus 9 times 3 is 27. So that's going to be the square root of 36. And that's going to make our r be 6. Now we can do an inverse tangent here to get the theta, but sometimes it's easier to do a sine or a cosine. And since we just found that the r is 6, we can see in our triangle down here in quadrant 4 that the cosine of theta would be 3, 6, which is 1/2. So that's going to make our reference angle the inverse cosine of 1/2. The angle whose cosine is 1/2 is going to be pi over 3. Because we're in quadrant 4, then we can either call it a negative pi over 3, or we could call it a positive 5 pi over 3, either way. So here now are going to be our different polar coordinates. If we choose a positive value of r, which we said was 6, then we could either use the negative pi over 3, or we could use the 5 pi over 3, since both of those are between negative 2 pi and pi. Then, if we extend this angle into quadrant 2, then we could also get to this same point by going through an angle that is going to be, I guess that would be 2 pi over 3 would put us into quadrant 2, and then a negative value of r, I keep trying to make that a 4, a negative value of r will shoot us through the pole and take us to that same point. And likewise, we could get to that angle in quadrant 2 with a negative 4 pi over 3. So these are our 4 answers, the 4 polar coordinates for that rectangular coordinate. So let's take a look at going the other direction. So now we're going to start with polars and get to rectangulars. And I'm just going to go with the formula. X is going to be our cosine theta. That's going to be negative 6 cosine of 7 pi over 6. So that's going to be negative 6. And cosine of 7 pi over 6, the reference angle is pi over 6. The cosine of pi over 6 is square root of 3 over 2. And because we're in quadrant 3, that's going to be a negative square root of 3 over 2. So that's going to make the x-coordinate be a positive 3 square root of 2. Y is going to be our sine theta. So that's going to be negative 6 times the sine of 7 pi over 6. And again, sine of pi over 6 is a half. In quadrant 3, that's going to be a negative 1/2. So that'll be a positive 3, making our rectangular coordinates 3 square root of 3, comma 3. And that's unique. Okay, now we're going to look at x being 1 plus I squared root of 3 and y being negative 2 squared root of 3 plus 2y. And we're going to find the polar form of xy. So first we're going to need to find the polar form of x and y. So the r for x is going to be the square root of 1 plus square root of 3 squared is 3, so that's going to be square root of 4, which is 2. And the theta is going to be, let's see, I'm going to draw it in quadrant 1. There's 1. There's square root of 3. We said the hypotenuse is 2, so the sine of that angle is 1/2. That's going to make our reference angle be pi over 6. So x is going to be 2 cis pi over 6. Similarly, the radius for y is going to be the square root of 2 squared is 4 times 3 is 12 plus 4 is 16. Square root of 16 is going to be 4. And if we look at this, it's going to be in, let's see, negative x value, positive y value is going to put us into quadrant 2. So we have negative 2 square root of 3, 2, and we said the r is 4. So the cosine of that angle is 2/4 or 1/2. That is going to make the reference angle be a pi over 3. But because we're in quadrant 2, that means our actual angle is going to be 2 pi over 3. So y is going to be 4 cis 2 pi over 3. So to find x times y, we're going to get the 2 cis pi over 6 times our 4 cis 2 pi over 3. That's going to be, we'll multiply the r values and we will add the angles. So getting a common denominator of pi over 6, that's 4/6 plus 1/6 is going to be, I can draw that, that's 8 cis 5 pi over 6. Part B, to put it in rectangular form, we're going to get 8 cosine of 5 pi over 6 plus 8I sine of 5 pi over 6. So cosine of 5 pi over 6, it's going to be a reference angle of pi over 6. That's going to be square root of 3 over 2. In quadrant 2, that'll be a negative square root of 3 over 2. And sine of that is going to be 1/2. And in quadrant 2, that will be a positive 1/2. So that's going to be a negative 4 square root of 3 plus 4i is going to be the rectangular form of x times y. Y divided by x, so we're going to take the y, which is 4 cis 2 pi over 3 divided by 2 cis pi over 6. So we'll divide the r values. That'll be 4 divided by 2, which is 2. And then we will subtract the angles. So 2 pi over 3 minus pi over 6. So this is going to be 2 cis. 4/6 minus 1/6 is 3/6, which is pi over 2. So there we are in polar form. In rectangular form, that's 2 cosine of pi over 2 plus 2i sine of pi over 2. So cosine of pi over 2 is 0, and sine of pi over 2, is 1. So that's going to get us to just 2i. And now we're going to do 1 over x. So we want 1 over x is going to be 1. So we want to think of 1 in polar form. So 1 is going to be right here on the real axis. So the angle is 0 and the r is 1. So that's going to be 1 cis 0. So that's going to be 1 cis 0 divided by, and our x was, I think, the 2 cis pi over 6, I believe. Is that what x was? Yep. Okay. So we have then, as before, 1 divided by 2 is 1/2, and we'll subtract our exponents. 0 minus pi over 6 will be a negative pi over 6, and so we could leave it that way is fine, or you could call it 1/2 cis 11 pi over 6, either way. And the rectangular form, we're going to go 1/2 cosine of a negative pi over 6 plus 1/2 I sine of negative pi over 6. So cosine of pi over 6 is square root of 3 over 2. In quadrant 4, that's still going to be the square root of 3 over 2. and then we'll get 1/2 I, and the sign of negative pi over 6 will be a negative 1/2. So in rectangular form, we're going to get square root of 3 over 4 minus 1/4 I is 1 over x. And now we want rectangular form of x cubed. So x cubed is going to be r cubed cis 3 theta. And since r for x was 2 and our theta was pi over 6, then we are going to get 8 cis, and that's going to be a pi over 2. Oh, and then we want to go to rectangular form, so I guess again we're going to get 8 cosine of pi over 2 plus 8i sine of pi over 2. Since cosine of pi over 2 is 0 and sine of pi over 2 is 1, that's going to be 8i. Okay, so this is kind of crazy, but our r e to the I theta is going to be r cis theta, crazily enough. So in our case, we're going to get 4 cis pi over 4. So that's going to be 4 cosine pi over 4 plus 4i sine of pi over 4. So cosine is pi over 4 is square root of 2 over 2, and sine pi over 4 is also square root of 2 over 2. So that's going to become 2 square root of 2 plus 2i square root of 2. Okay, the fourth roots of negative 16i. So we are going to think of if x is the fourth root of negative 16i, and x we're going to think of in cis form as being r cis theta, then x to the fourth will equal negative 16i. So writing both sides of this equal sign now in polar form, in cis form. So the x to the fourth is going to look like r to the fourth cis 4 theta, and we're going to try to write negative 16i in polar form. So negative 16i is going to be down here. So it's r, that distance it is from the pole is going to be 16. We want the r to be positive. The angle that it takes to get there is going to be 3 pi over 2. So we're saying this is going to be 16 cis 3 pi over 2. So that means r to the fourth must be 16, and 4 theta must be 3 pi over 2 plus 2 pi times k, where since we have fourth roots, we can get a total of 4 different answers. So k can be 0, 1, 2, or 3. So again, taking the fourth root of 16, we want to keep the r positive. So we'll choose the positive 2 fourth root of 16. Dividing through everything here by 4, we're going to get theta is going to equal 3 pi over 8. And then we'll get plus, and then 2 pi divided by 4 will be pi over 2 times k, where k can be 0, 1, 2, or 3. So we're going to get that one root is going to be the 2 cis, and we'll choose the k to be 0 and get 3 pi over 8. Our 2 is going to be 2 cis. If we add pi over 2, which is 4/8, that will be 7 pi over 8. Our third one, adding another 4/8, is going to be 2 cis, 11 pi over 8. And our final one is going to be 2 cis, 15 pi over 8. And these are messy, not ones that we know, so we'll just leave it in polar form. If the angles turn out to be nice enough that we can do them without a calculator, I would probably ask you to do the rectangular version of them as well. So now we're going to find the angle theta between these two vectors and round to the nearest tenth of a degree. So we're going to use the fact, we're going to use our dot product. So cosine theta is going to be V dotted with W over the magnitude of V times the magnitude of W. So V dot W, we're going to get 3 times -1 plus 1 times 4 over the magnitude of V is going to be the square root of 9 plus 1, and the magnitude of W is going to be the square root of 1 plus 16. So that's -3 plus 4 is 1 in the numerator. Looks like square root of 10 and square root of 17. We can just go right to our calculator, or this one's not too bad to do, square root of 170. So that, remember, is cosine of theta. So now we're going to walk it to our calculator and take the inverse cosine of 1 over the square root of 70. When I do that, I'm getting 85.601, or to the nearest tenth, that's going to be 85.6 degrees. Okay, let's see if we can find parametric equations for the position of a particle at time t if the particle is at -3, 5, at t equals 0, and has a uniform velocity of 2, -3. So we don't really need a picture, but if it helps, we're going to start at this point right here. I'm going to call that point A. We've got a direction vector of 2, -3. So if we go over 2 and down 3, then we're going to go this much every time we increment t by 1. So to get the position of the particle, we're going to get that xy is going to be, we can think of that as being the vector OA, going from the origin to that point A, and then plus t times our direction vector or velocity vector to -3. That's a vector equation. So from that, we can see that OA is our -3, 5. Whoops, I'm going to keep that in vector form for now. It doesn't really matter. And then t times, boy, the plus signs and t's are hard to distinguish, plus t times that 2, -3. So in parametrics, we're going to get -3 plus 2t, and y will be 5 minus 3t. So there's our parametric equations. The speed is going to be the magnitude of the velocity vector. So that's going to be the square root of 2 squared is 4 plus 3 squared is 9. So that's going to be square root of 13 for our speed. And the Cartesian equation for the path means we're going to eliminate the parameter here. So we can say adding the 3 to the other side and then dividing by the 2 is going to give us x plus 3 over 2. Or if we like, we can call that 1/2 x plus 3/2. We can plug that into the y parametric equation and get 5 minus 3 times 1/2 x plus 3/2. So that's going to be 5 minus 3/2 x, and that looks like a minus 9/2. So we're going to get y equals -3/2 x. 5 is 10/2 minus 9/2 will be a plus 1/2. There's the equation of that line. That is the path of our particle. Okay, let's see if we can graph this one. So the first one here is going to be a rose curve. So because the r is the 2, then we know that the furthest the curve will ever be from the pole, or the origin, is going to be 2. So I'm going to put a dotted circle of radius 2 to use as a guide. Now, the first pedal is going to be when sine 5 theta is first equal to 1. That's going to be when that angle is first equal to pi over 2, because that's when sine is equal to 1 is at sine of pi over 2. Dividing by 5 means our first leaf, or first pedal, is going to be at pi over 10. So I'm going to come over here and say there is theta equals pi over 10, and I'm going to go ahead and put a point down there. Then our spacing between pedals is going to be 2 pi divided by the number of pedals. Since our n is odd, that is the number of pedals. If that had been even, we would have had 2n pedals. So our pedals are going to be 2 pi over 5 apart. That's 4/10. So that's going to make our next pedal be pi over 10 plus 4/10 is 5/10. So that's going to be here at theta equals pi over 2. That's going to be the end of our next pedal. And then we're going to add another 4/10 to that. So that's going to be 9/10. So we're going to be over here at theta equals 9 pi over 10. And that's going to be another endpoint of that pedal. Adding 4/10 to 9/10 is 13/10. I think it's going to be something like about there. It's going to be 13 pi over 10. And there's the fourth pedal. And adding another 4/10 will be 17/10. So it's going to look like it's kind of making a big star. So there's 17 pi over 10. So in the way you're supposed to draw this, although there's no way for me to see it because I'm not going to watch you do this, is if you imagine starting at the first pedal, looking 180 degrees, and then going counterclockwise to the next end of the pedal. I'm going to connect those two going through the pole. So I'm going to try to go through the pole to there, and then likewise through the pole to there, and through the pole to there. Kind of makes you draw the pedals, I think, a little more narrow than if you do some other way. And so there we go. Oh, beautiful. Okay, next one is going to be, so this is a rose curve with 5 pedals. The second one is going to be a limacone, and since this number is bigger than that number, it's going to actually be a looped limacone, or a limacone with an inner loop. So let's see, we're going to need to get the values of r when theta is 0, pi over 2, pi, and 3 pi over 2. And then we'll try to graph this. So when theta is 0, we're going to get cosine of 0 is 1, 1 minus 2 is -1. So that means on the angle 0, we're going to go back through the pole and plot the point right there. And we're going to label these with rectangular coordinates, which in the first case is no different than the polar coordinates. At pi over 2, cosine of pi over 2 is 0, so the r will be 1. So on the angle pi over 2, we will go up 1. That's going to put us right there. And that's going to be 0, 1 in rectangular. So, whoops. At pi, cosine of pi is -1 times -2 is 2 plus 1 is 3. So r is going to be 3 on the angle pi. So that's going to put us right there. And we'll label that -3, 0. And at 3 pi over 2, cosine is 0 again. So that's going to be 1. So on the angle 3 pi over 2, we're going to come 1 away. And we'll label that point 0, -1. So starting at 0, so we're starting at this point. We're trying to get here by the time we go through an angle of pi over 2. So somewhere along the way here, as the r values go from a -1 to a +1, it must go through 0. So we're going to connect these by going through 0. Then it'll just gradually get bigger until we get to there. Then the r values will gradually get smaller till we get here. And now again, we're going from an r value of 1 to an r value of -1 when we get back to 2 pi. So we're going to go through the pole to connect back to there. And there's our looped limacone, or limacone with an inner loop. Okay, here we go. Babe Ruth hits a baseball 4 feet above the ground with an initial velocity of 160 feet per second at an angle of 24 degrees above horizontal. Can we find parametric equations to model the path of the ball? Okay, so let's see. Here is our spot that's 4 feet above the ground, and that ball is going to take off at 160 feet per second. That's going to be the magnitude of that vector, and this angle is going to be 24 degrees. So we know that in terms of x, we're going to say there is no air resistance, and so the component of that vector that is going in the horizontal direction, so that part right here, is going to be 160 cosine of 24 degrees. That's how much of that 160 feet per second is going in the horizontal direction. And there's nothing impeding its progress because we're not going to take into account air resistance. So we're going to say that's going to be 160 cosine of 24 degrees times t is going to be our motion in the horizontal in the x direction. The component of that vector that goes vertical, that y component, is going to be 160 sine of 24 degrees. So the y component is going to be parabolic, so it's going to end up looking like, so we can kind of do a differential equation real quick if you need to. So acceleration due to gravity is a -32 feet per second, so that's going to be our second derivative of y. And so if we integrate that, we'll get -32t is plus c. Some constant is going to be dy dt. And if we look at the initial condition, the velocity in the y direction at time 0. So our velocity at time 0 is going to be our 160 sine of 24 degrees. So that's going to make that -32t plus 160 sine of 24 degrees is going to be our, that's actually velocity in the y direction, which we can think of as dy dt. If we integrate a second time, we'll get 1/2 t squared times -32 will be a -16t squared. We'll get that constant 160 sine of 24 degrees times t plus another constant. That's going to be our position in the y direction. We know that our height at time 0 when we hit that ball was 4 feet. And so plugging in 0 for the t's is going to tell us that constant is 4. So our y is going to, our parametric equation y is going to be a -16t squared plus 160 sine of 24 degrees times t plus 4. Okay, so there's part A. There's our parametric equations. Okay, and we want to know, when does the ball hit the ground? Well, when we're looking for t, it's going to hit the ground when the y, the height, is 0. So we are going to try to solve this. And what I'm going to do is I'm going to pause the video here and go to my calculator, And in rectangular coordinates, I'm just going to graph this as y1 and then see if I can find the 0. So this is going to be a parabola that opens down. So we know this thing is going to be a parabola, and we're trying to find out the when is going to be the t-value when that hits the ground. Okay, I'm going to pause it. So when I did this, I had to play around with the window a little bit. So what I ended up choosing is for the X window, I went from 0 to 20, and I made the scale 10. And for the Y window, I went from 0 to 100, and I made the scale 50 just to keep it smaller. So when I did that, I got the t-value to be 4.128. Now that's going to be in seconds. So that's when our ball hits the ground. Now, how far away did it land? Now we have to find that x value. So we're going to take our t value of 4.128, but I'm going to use the exact answer off the calculator and plug it into our x of t, that 160 cosine 24 degrees times our 4.128, and I'm getting 603.368 feet. So that thing got hit a long way. Okay. Let's see, is that it? I think that's everything.